Okay, so in this video, we will use the fundamental properties of logarithms to simplify the log of a very complex expression into sums and differences of a much simpler logarithms. But first, let's look at a general example. So what if we look at the log, and here I will omit the base as the argument does not depend upon the base. So if we take the log, say, of AB over CD, the question is, can we decompose this single logarithm into 4 separate logarithms, one for each of the 4 terms? And although I'm using a single product of 2 terms on top and on the bottom, you will see the argument does generalize for any product on top and on the bottom. So there could be 20 terms on top, 50 on the bottom. The argument will work just the same. But for simplicity's sake, we are going with 2 terms on top and on the bottom. So let's think of AB as a single term and CD as a single term as well. We have the log of a quotient. We know that this is the log of the top minus the log of the bottom. We can now use another property of logarithms. In each case, we have the log now of a single product. The log of a product is the sum of the individual logarithms. But for the second term, you have to be careful. The negative applies to this log, and we're about to break up the log into 2 separate pieces, and they are both multiplied by -1. So open up here your parentheses, and the log of C times D is of course the log of C plus the log of D. And now if we distribute the negative sign, we obtain the desired result. You see that we have broken down this single logarithm into 4 separate logarithms, and you see that every term on top gets a positive sign, and every term on the bottom gets a negative sign, and this always works. So if you have the log of, say, 20 terms on top over 30 terms on the bottom, you'd have a sum of 50 logs, one for each term on top and on the bottom. Every term on top gets a positive sign, and every term on the bottom gets a negative sign. And this always works in the same fashion. So let's now look at an actual example, and we will take advantage of what we've just discovered, and we will skip these steps and jump straight from the single log to the full decomposition into sums and difference of logs, one for each of the original terms in the expression. So what if we look now, as we have an example, we'll take a base, the log base 2 of the 5th root of x squared plus 1 times 8 to the sine of x over x to the 6 times cos of x. So we have, just as in the general discussion, the log of a product over a product. So we can right away go from here to here. So what will this become? Well, we'll get the log base 2 of, and here let me replace the 5th root by a power of 1 over 5. And you'll see why in a second. So this is x squared plus 1 to the power 1 over 5. This term's on top, so it's a plus log base 2 of 8 to the sine of x. These terms are on the bottom, so they get negative signs, so minus the log base 2 of x to the 6. On the bottom as well, negative sign as well, minus the log base 2 of cos of x. So we've broken down the log of this massive expression into 4 much simpler logarithms. Now we can simplify a little further. using other properties of logarithms. Now this one is very simple. We have the log of an exponent. We know we can take the exponent out as a constant multiple of the log, so this would be 1 over 5, times the log base 2 of x squared plus 1. This one is a little bit more interesting, right? We have a logarithmic function base 2 and an exponential function base 8. But 8, if you factor it, is 2 cubed. So let me write this here. So we have 8 to the sine of x equals, factoring 8 as 2 cubed, so 2 cubed to the sine of x. But now we have a double exponentiation. We have 2 to the power of 3 and the whole thing to the power of sine of x. But we know that when we double exponentiate, we can combine the two exponents by multiplying them out. So 8 to the sine of x is the same as 2 to the 3 times sine of x. And now with this observation, we can match the base of our exponential with the base of our logarithmic function. Minus. We can take advantage here of the same property that we took advantage of in the first case. X to the 6, we can move the 6 up front as a multiple. And here this is as simple as it gets, minus the log base 2 of cos of x. And so our final simplification is on the second logarithm. And it's a very simple simplification, canceling the logarithmic function base 2 with the exponential function base 2. And so we're left with 3 times sine of x minus 6 log base 2 of x minus log base 2 of cos of x. And we've done it. We've decomposed the log of this massive expression, right? A quotient of two products into a sum and difference of much simpler individual logarithms. In one case, the logarithm vanished completely. And you might wonder, why is this useful? Well, this will be useful when we get to thinking of differentiating something of this form. If you were to differentiate this directly, this would be a rather nasty problem. But if you break it down before differentiating into 4 separate, much simpler expressions, the derivative of this now becomes a lot simpler. And that's it.